Physicists often describe theories as beautiful when they elegantly explain a wide range of phenomena with simple concepts and mathematics. Take Einstein's general relativity. Its core equation can be written in a single line. The standard model of particle physics, however, is anything but simple. Its equations span pages, and some elements seem arbitrary, almost unsettling. It is as if we have patched together a framework that works but feels incomplete. Deep down, we know something is missing. There's a sickness in our theory. The standard model is an impressive achievement. It describes the fundamental particles and their interactions with remarkable accuracy. But there's one glaring problem. If you write down its equations, they suggest that no particle should have any mass. And yet, we live in a universe where objects clearly possess mass. Without it, there would be no stars, no planets, no life. This contradiction meant that something fundamental was missing from our understanding of nature. We take mass for granted. It's what makes objects solid, what gives them weight. But what is it really? For centuries, mass was simply a given, an inherent property of matter. But physics demands deeper explanations. Why do some particles have mass while others, like photons, do not? If we could answer this question, we would unlock one of the deepest mysteries of the universe. There was a time in the earliest moments after the Big Bang when particles had no mass. They zipped through the universe at the speed of light. And then, something happened. A mechanism turned the intangible into the tangible. It was as if an invisible force field stretched across the cosmos, whispering to some particles, "Stop, feel your weight." This is the story of how mass was born. In 1964, a British physicist named Peter Higgs took a walk in the Scottish Highlands. It was on this solitary journey that inspiration struck. He imagined a new kind of field, one that permeated all of space, interacting with certain particles and endowing them with mass. This was the Higgs field. The Higgs field is everywhere. It surrounds us, fills the vastness of space, even exists within us. Some particles, like quarks and electrons, interact with this field and gain mass. Others, like photons, pass through unaffected. It is an invisible ocean, giving substance to the fundamental building blocks of the universe. In quantum physics, every field has an associated particle. If the Higgs field truly exists, there must be a particle linked to it, the Higgs boson. If we could find this elusive particle, we would confirm the mechanism that gives mass to the universe. But there was a problem. No one had ever seen it. The search for the Higgs boson became one of the greatest quests in physics. Some called it the God particle, a name both loved and loathed by scientists. It was an attempt to describe its fundamental importance. If this particle existed, it would explain why everything else has mass. Physicists around the world embarked on an extraordinary hunt. They built powerful particle accelerators, machines that could smash protons together at nearly the speed of light. The idea was simple: create conditions similar to those moments after the Big Bang and see if the Higgs boson emerged. For years, Fermilab in the United States led the search with its Tevatron Collider. It was a tireless effort. Night and day, particles collided, data was analyzed, yet the Higgs remained elusive. The frustration grew. Billions had been spent. Thousands of scientists dedicated their lives to the search, and still, no sign of the God particle. As hope at Fermilab faded, a new machine rose in Europe. The Large Hadron Collider, LHC, the most powerful particle accelerator ever built, was ready to take the search to the next level. Located deep beneath the border of France and Switzerland, this immense ring of technology could achieve unprecedented energies. If the Higgs boson existed, this was where it would be found. Inside the LHC, protons raced around a 27-kilometer loop, colliding with unimaginable force. For an instant, conditions mirrored those of the newborn universe. If the Higgs boson was there, these experiments would shake it loose from the fabric of reality. Then, in 2012, the moment arrived. Scientists at CERN announced they had found something, a particle with a mass of about 125 giga-electron volts, behaving exactly as the Higgs boson should. Decades of effort had led to this discovery, a confirmation that the Higgs field was real. The mechanism giving mass to the universe had been unveiled. This discovery was more than just a missing piece in the Standard Model. It was proof that our understanding of fundamental physics was on the right track. It validated the framework that explains why matter exists in its current form. And yet, it also raised new questions. Is the Higgs field alone enough to explain mass? Are there deeper layers of reality still hidden from us? The Higgs boson was found, but physics is far from complete. The Standard Model, even with the Higgs, doesn't explain everything. Dark matter, dark energy, the nature of gravity at quantum scales, these remain unsolved. The search for knowledge continues. As we peer deeper into the fabric of the universe, we may yet uncover forces and particles beyond our wildest imagination. The discovery of the Higgs boson was a triumph, but physics is an endless frontier. Perhaps one day another physicist will take a walk, just as Peter Higgs did, and stumble upon the next great revelation. If you love exploring the mysteries of the universe, subscribe to the channel and join us on this incredible journey. There's so much more to discover, and together we'll continue to unravel the secrets of the cosmos.